Hello, general chemistry students. This is week 3, and in this week we are going to be looking at SLO 5.2. And SLO 5.2 will be all about the second law of thermodynamics. And so the second law of thermodynamics really describes processes that are spontaneous. So the first video here, we're going to be talking about this idea of spontaneity and how do we determine if something's spontaneous or not. Right, so a spontaneous process is really one that proceeds without outside intervention. So for example, if we look at the figure on the right, we have two containers, one filled with 1 atm of gas and one that's evacuated, so 0 atm of vacuum. If we were to open up the stopcock and let the gases mix, that gas, the high pressure side, is going to flow into the low pressure side. And this expansion of gas is what's called a spontaneous process, meaning we don't have to add any energy in order for this process to happen. Alternatively, the reverse reaction is not spontaneous. One cannot just move the gas back after it has mixed and reached an equilibrium. All right, so another example of a spontaneous process, really here we're showing an egg that's dropped and it breaks. The reverse reaction is not spontaneous, meaning it can't reform again and go back into this person's hand. All right, so the spontaneous process many times is not spontaneous in the reverse direction. Another example of a spontaneous process is if we had this flask of ice water, and this will be governed by the temperature at which that ice water is at. So if the temperature is above 0 degrees, what's going to happen here is that the water is going to melt. The ice is going to melt to water. But if we're below 0 degrees, the ice water will not melt. Okay, so it just depends on the temperature. Spontaneous greater than 0, but not spontaneous. But it's not going to be spontaneous in the reverse direction. All right, so let's think about how this works. So we have these molecules of water and dye, and we're going to mix them together. So in this beaker, we have this blue dye. We're going to put a couple drops of it into the beaker. But what we want to do here is we want to look at it on the molecular level. And so on the right, you see all our water molecules and then the dye molecules in blue. All right, the question is why is it that when we put that blue dye into water, why does it mix? And when the dye mixes, what are the arrangements of the unmixed dyes? Right, so we're going to do kind of a thought experiment. We're going to have a flask, and in this flask we're going to put 4 molecules. 2 molecules of water and 2 molecules of dye. How many possible arrangements can we make when we have 2 molecules of each? All right, so we have our 2 dye molecules. They're going to be represented by the red dot, and we have water molecules represented by the pink dot with the 2 black dots. All right, so how can we arrange this? So this is going to be our unmixed state, where they are completely separated from each other. But we could also move them, and this is another arrangement that is distinguishable, meaning it's different from the one above. So these molecules have mixed. Right, so how many distinguishable states can you come up with? So here we're showing 6. And in those 6 states, only one of those is unmixed. All right, so what we started with, so the 2 dye molecules on top and the water molecules on the bottom, all of the other states are distinguishable from each other. And the ones that are distinguishable from the mixed state will be considered the unmixed state. Or sorry, the unmixed state is what we start with, while the others are mixed. And so in this system, and it's more likely that the state is mixed and not unmixed. Right, so imagine we're going to increase our system. Now we have 9 molecules, 3 dye and 6 waters. And if we take all of these possible arrangements, we would end up with 84 distinguishable different arrangements. Right, so what this says is that the number of molecules increase, the number of distinguishable arrangements in the mixed state increases. So there's more ways to arrange the molecules than in the unmixed state. So the probability of having the mixed state increases. And so we're going to really define that probability, the possible arrangements, the more of those possible arrangements as having a higher entropy. Okay, so that is it for our first video for SLO 5.2. Thank you.